All right, so today, 9-5 functions and their inverses. So we're going to determine whether the inverse of a function is a function, and then we're going to write the rules for inverses of functions, okay? Which we've done before, right? We did some work with inverses in Chapter 7 when we were doing logarithms. We did some stuff with inverses. So talked about it in Lesson 7 too. And back in Lesson 1-6 in Algebra B, we did the vertical line test. And we're going to look at, today we're going to look at what's called the horizontal line test to see if the inverse is a function. Okay. So what's the vertical line test tell us? If it's vertical, right, okay. But what does it tell us? If it's a function now, okay, because if it intersects more than one point, then the relation is not a function, okay. But when we do the horizontal line test then, if it intersects more than one point horizontally, then the inverse would not be a function. So vertical line test tells us whether it's a function or not. Horizontal line test then is going to tell us whether the inverse is a function or not. So here we have example 1. We're going to do the horizontal line test for this. All right, so I'm going to draw me, make a horizontal line here. All right. Okay, so letter A is the, or let's say the, letter A is the blue line. Okay, so will this blue line pass the horizontal line test? Yes, it is. Okay, so the blue line, so for the blue line, the inverse is a function. Okay, how about the red line? Okay, because we've got quite a few places here where if it crosses more than one point horizontally. So for the red line, the inverse is not a function. Okay, and that right there is the how we do the horizontal line test. If you recall from lesson 7-2 that to write the rule for the inverse of a function, you can exchange x and y and solve the equation for y. Because the values of x and y are switched, the domain of the function will be the range of its inverse and vice versa. So that's one of the things we need to remember. So we're going to find the inverse of this function, cube root of x plus 1, and determine whether it is a function and state its domain and range. So first of all, let's graph the function to make sure that the inverse is a function. So go ahead and put it in your y equals. Oops. And let's see how we'll just graph it. So where do you find the cube root? How do I do the cube root on my calculator? Yeah, if you go to math, there is a button for cube root. Number 4 does cube root. If you want to do some other root, you could do number 5. All right, so number 4 there, and x plus 1, and zoom 6. What do you think? Will that pass the horizontal line test? Okay, so we've determined there that the inverse is a function. There's our graph. Okay. Okay. So now we're going to go ahead and switch x and y and solve for y to find the inverse then. So we'll have x equals the cube root of y plus 1. So I want to find this inverse, and so what do I do now? All right, because we want to get rid of the cube root, so we're going to go ahead and cube both sides. So we get x cubed equals y plus 1. And then we'll subtract 1. Now, the only thing different is here is that it's a function, right? How do I write it in function notation? What? That's right, f negative 1. So f inverse of x equals x cubed minus 1. So that would be our inverse. Okay. Since it is a function, then we have to write it in function notation. If it was not a function, then we would just say y equals. Okay? All right. Now we need to determine the domain and range. Well, if we look at our original, right, we get the cube root of x plus 1. Does this graph here, does it ever stop moving from left to right? No. Okay, so our domain is all real numbers, which means if the domain of this one is all real numbers, that means the range of the other one is good. Okay. All right, and what about the range for this one? What about the y values? Does it ever stop moving up or down? No, it doesn't. So the range there would be all real numbers, which means the domain here would be all real numbers. Okay, good. All right. Very good. Of course, we should know that. We have x cubed for our function that we got, and that goes forever vertically anyways. Okay, good. So that's just a little review, right? Something we've done before. So here you go. So you've seen the inverse of functions are not necessarily functions. When both a relation and its inverse are functions, the relation is called one-to-one. In a one-to-one function, each y value is paired with exactly one x value. So if we have, basically what it means is that we start out with a function. Okay, so our original is a function. If it passes the horizontal line test, then the inverse is a function. So if both the original and the inverse are functions, then they have to be one-to-one. You can use composition of functions to verify that two functions are inverses. So we're going to use what we did yesterday with composition to verify whether two functions are inverses or not. And so here's what's going to happen, is that if the compositions of two functions equal the input value, which is x, then they are inverses. So here they show us a quick example here. They say f of x equals 3x and g of x equals 1/3 x. They do f of g of x, it simplifies to x. Do g of f of x, it simplifies to x. And if they simplify to x, then they are inverses. Now here's the thing. So we're going to do f of g of x, and we're going to do g of f of x. You got to do both. All right. If it satisfies one, it's probably going to satisfy the other one, but you have to check it. You have to prove it, okay? But if it doesn't satisfy the one, you don't have to do the other one, okay? So you can disprove it only one way, but to prove it, you got to do it both ways. Right. So we're going to determine whether these functions are inverses. All right, so first of all, it looks like I've graphed the line here. Which one of these two lines have I graphed? Where's the y-intercept on this line here? At -1, which means it would be this one here, right? 3x minus 1. Okay. All right, so if we graph 1/3 x plus 1 on there, let's see what happens. So 1/3, so we have a y-intercept of 1. And the slope of 1/3, which means I do what? We'll go up 1 and over 3. So we'll go up 1 over 3. And if I draw the line through them, right, we need to determine whether those are inverses or not. Do they look like inverses? Possibly, okay? But here's the thing is when I do the composition, I have to get x, right? Well, that means then if I drew in the line y equals x, let's see, if I start here, then it should go, when I draw that line in, the intersection point of those two other lines should be on the line y equals x. Okay? So by looking at this, I can pretty much say that no, they're not going to be compositions, but I have to check it mathematically. Okay? So we'll do g of f of x, or f of g of x. We'll do that one first. F of g of x. Okay? Just like we did yesterday. So we're going to take 1/3 x plus 1 and put it in for x and f of x. So we'll have 3 times 1/3 x plus 1 minus 1. All right, and if they are inverses, then this will equal x when I'm done. Okay, so we need to distribute. 3 times 1/3 is 1. Okay, so we get x. 3 times 1 is 3. Okay, all right, and this equals x plus 2. All right, but x plus 2 is not equal to x, so they are not inverses. All right, and we showed that graphically and then also algebraically. So I did f of g of x, disproved it, so I don't need to do g of f of x. Okay? But if it was true for f of g of x, then you would have to do it for g of f of x also. Does that seem pretty simple for the most part? Okay. If you can do the composition, then it shouldn't be too bad. Okay. All right, so let's